This lesson on simple electronic devices will cover an introduction to transistors. Here is a photo of three different types of transistors. Note that each one has three contacts or three input leads. A small signal applied to one of the leads allows us to control a much larger current between the other two leads. There are several different types of transistors. One way that we might characterize them is by the power level that they can handle. Another distinction is their mechanism of operation. We will look at just a few different mechanisms. Transistors are the principal building block in all integrated circuits. Discrete transistors, such as these shown here, are used in a variety of applications, such as amplifiers and switching devices. The discussion of transistor amplifiers for applications like music is beyond the scope of our work in this course. We will instead concentrate on their use as switches here. The earliest commercial transistors were called bipolar transistors. They are also known as junction transistors. Basically, a bipolar transistor is a sandwich of N-type and P-type semiconducting material. Let's first look at the NPN transistor. Notice the very thin layer representing the base made of P-type material. The collector and emitter made from N-type material are very much bigger and are heavily doped so that they have lots of charge carriers, lots of electrons. The base, on the other hand, is very thin and lightly doped, so is poor in charge carriers and therefore has a high resistance. There are multiple ways to configure a transistor in a circuit. We'll look at one very widely used example. Before the transistor is turned on, there is no bias, so there is a potential energy barrier across each junction. To make the transistor turn on, the base emitter junction is forward biased. There's also usually a large positive voltage applied to the collector through the load, represented by resistor R1 here. When the transistor is turned on, the potential at the base emitter junction collapses because it is forward biased. I'm showing a battery here connected through a resistor to the base for simplicity. Normally, some signal would be providing a forward bias from the base to the emitter. Let's take a closer look at the base. The large positive voltage attached to the collector draws electrons away from that side of the base collector junction. When the base emitter voltage is forward biased, electrons are drawn away from the base toward the outer circuit. The holes left behind attract electrons from the emitter to cross the junction into the base. A very few of these electrons recombine with holes inside the base. However, because the base is so thin, many of the electrons are swept away into the collector. In fact, many times more of the electrons move across from the emitter to the base to the collector than recombine with the holes. This means that the current between the emitter and collector is many times larger than the current between the base and the emitter. The emitter-collector current follows the same pattern in time as the variations in the base emitter current, but the emitter-collector current is much larger. Hence, the pattern of the current signal has been amplified. Here's the schematic symbol that represents a bipolar NPN transistor. The arrow in the symbol points in the direction of forward biasing the base emitter junction. Recapping again, a small voltage across R2 produces a small current between the base and the emitter. This sweeps the electrons from the emitter through the base to the collector. Therefore, a large current flows from the collector to the emitter. This is analogous to turning a control valve to open the flow through a pipe or closing a switch to provide a path for a current to flow from the collector to the emitter. The story for a PNP transistor's operation is similar, but the forward bias voltage and the current directions are reversed. Field effect transistors operate on a different set of principles. Once again, there's a large variety among these devices, but we will focus on just a couple examples. The most common of these is called a metal oxide semiconductor field effect transistor. People use the acronym MOSFET or MOSFET for short. In a MOSFET, a voltage signal is applied to the gate, either increasing or decreasing the number of charge carriers in a channel between the source and the drain. If the device is designed to increase the number of charge carriers when a signal is applied, then it is called an enhancement mode device. Although it is built on a p-type substrate, this device is an N-channel device. The name comes from the fact that negative charges, or electrons, must be recruited to form a channel for current to move from the source to the drain. The p-type substrate is lightly doped. It has a very high resistance initially because of a lack of charges in the region between the source and the drain. If the source is connected to the negative side of a battery or power supply, then electrons can move into the source, but they are trapped there. Now imagine that we apply a positive voltage to the gate. Positive charges build up on the metal contact, but go no farther due to the non-conducting metal oxide represented by the yellow region. However, like a capacitor, the positive charges attract electrons to the other side of the oxide layer. Eventually, these electrons experience the field between the drain and the source and migrate toward the drain. The net effect is a channel of current between the source and the drain. An N-channel enhancement mode MOSFET is one of the most common varieties. The schematic symbol looks like this. The control signal is a positive voltage applied to the gate to turn on the transistor. The battery shown here is just a reminder it's not a practical way to turn on the MOSFET. When the gate gets a positive voltage above a small threshold, the resistance between the source and the drain drops and current flows between the source and the drain. And for power MOSFETs, it can be on the order of several amps of current. And that can be very useful for driving heavy loads like motors. This example achieves two big advantages. First of all, we have a voltage control of a current. Voltages are easier to implement than current control. And secondly, we have a signal going into a gate that has a very high input impedance. That means the gate will not draw much current from the signal, and there's less chance of distorting the signal.